Let me get started. I'm Chungeun Yoon, working at the KDI School, and today I'm presenting my working paper titled Inventors and Farm Innovation, Evidence from the US World War I Draft. As argued by many economists, innovation is one of the key drivers of long-term economic development, and farms are a crucial source of innovation. For example, they account for more than 80% of patents over the last decades. And to do this innovation activity, firms typically hire or work with high-skilled workers, such as individual inventors who hold patents. Thus, the inventor's human capital is one of the most important inputs in the firm's knowledge production function. But understanding how inventors' human capital affects the firm's knowledge production is complicated because there are many different mechanisms. The first, the inventors help the firm innovate by working directly with the firm. Second, other inventors that can generate the knowledge spillovers affecting the firm indirectly. As one instance of the second case, consider inventors working in the same geographical location. As another instance of this second case, consider inventors working in the same industry producing knowledge spillovers. But inventors do not necessarily always produce knowledge spillovers. They can compete with the firm as an entrepreneur or work with the rivals of the firm in a way that might reduce the firm's knowledge production. Then, how can you understand the importance of inventors' human capital on firm innovation in such a variety of mechanisms? One solution is to investigate the firm's innovation when a firm exogenously loses inventors. What happens to a firm innovation when we pull out inventors from the firm and those inventors cannot work with anyone anymore? And this effect of shock to the labor supply of inventors is not obvious because inventors do not necessarily work for a single firm. For example, they can work work alone as an entrepreneur, or in a team with other individuals, or even they can work with several firms. Moreover, inventors that may have a positive effects on each other's inventions based on the knowledge spillovers and human capital externalities. But inventors that may have a negative competition effect on others' inventions. Max Planck, who was awarded the Nobel Prize for the physics in 1917, mentioned that new generation grows up when its opponents disappear. So far that we have a little evidence how a supply shock affects innovation activity at the firm level. Most of previous the studies focus on instead on the impact on individual knowledge producers, such as inventors and researchers, and focus on the knowledge spillovers in geographic space. And thus, understanding the impact of inventors on firm innovation is an empirical question. And I introduce a new method, a new natural experiment, and new data to answer the following research question. What happens to a firm's innovation rate measured by its patent application when a firm exogenously loses three conceptually different types of inventors due to the US World War I draft and military service? The first, I consider inventors working with the firm in a collaboration space. I measure the effect of the loss of inventors working with the firm. And second, I consider the inventors working in the same geographical location. I measure the effect of the losing inventors outside the firm, but working in the same county where the firm is located in geographic space. And finally, I consider inventors working in the same industry And I measure the effect of the losing the inventors outside the firm working in the same, the idea of space, working on the same topics. And I exploit a new natural experiment of the World War I draft and military service to identify the causal effect on firm level innovation. I create a data set that consists of the pattern data, US census, and World War I military records through the matching procedure. Specifically, I employ a defensive strategy. So I compare firms which are likely to lose inventors versus other firms which are unlikely to lose inventors. And I find the three main results. The first, I find that the losing inventor team members that are working with the firm that decreases the firm's invention. And second, the losing the other inventors that are working in the same counties, the same geographical location, does not significantly affect the firm's innovation activity. And third, losing inventors that outside the firm working in the same industry in the space of ideas actually increases the firm's inventions. And taken together, I provide a new evidence that new ideas grow up when there is a less competition in the field. And this work contributes two groups of literature. I focus on the effect of supply shock on firm level innovation rather than individuals. And this study also inspired by my previous work that studies the causal relationship between labor supply by immigrants and innovation. And second, I focus on the inventors, the human capital as a determinant of firm innovation. And for example, that there is a large literature about how R&D investment, tax credits, and other inputs affect the firm innovation, but there is a less study about how inventors' human capital affect the firm innovation. Asimoglu developed a theoretical model, but there is a few empirical studies. Now, let me spend a couple of minutes to explain about the US World War I draft and lotteries. To construct the value treatment and control groups is crucial to understand which firms are likely to lose inventors and which firms are unlikely to lose inventors. This short video clip shows the President Woodrow Wilson actually draw a number in draft lottery. Yeah, I hope the you saw that this short video clip clearly. And yeah, as you can see, when the U.S. entered the war in 1917, the men in draftable age groups were required to register in local draft board and were issued a draft registration card with a registration number. So more than the 4,000 local draft board existed. Then the more than the 4,000 men whose registration number there were the more than the 4,000 men, and next the 4,000 men that had a registration number of 2 and so on. Okay, and let's suppose a registration number of the 38 was drawn in the draft lottery. Then about the 4,000 men whose registration number of 38 were drafted in each the draft board.
Chungeun, sorry if I interrupt you. There is one clarifying question by Matt Cummins. Matt, if you want, you can ask the question directly. Unmute yourself. Yes.
Sure, great. Yeah, I don't mean to interrupt for very long. I'm not an economist, so maybe everyone else on this call already knows this. I just wondered, given that this is an empirical exploration and people haven't done it before, is there some sense of what prior literature would predict, even if people hadn't explored it, especially when you were talking about the loss of these 3 kinds of inventors?
Oh, say that again. So
you can read it also in the chat box, Chungeun Yoon.
Yeah, I couldn't see the hear clearly, so sorry about that. Moderate this. Okay.
Yeah, it's always difficult to get to the chat box. I can read it out. What does prior literature predict a
I
losing?
see. I saw your the chat now. Okay. So actually, the Max Planck the pointed out that some the negative competition effect. So some of the literature that argue that yeah, most of the literature actually support the knowledge, positive knowledge spillovers rather than the negative competition effect. But as I mentioned, the Max Planck suggested some evidence that okay, so if you have the large number of the peers or your colleagues, so there is a large competition in your field, so you are the less likely to the public or you have the get attention because of the competition. So I think that's the large based on his argument. Okay. Yep. Any question?
You can go ahead. Thanks.
Yep. And yeah, so this shows the first 100 drone. So it means that about the 4,000 men whose registration number of the 258 were first drafted, and the U.S. When U.S. entered the war in 1917, and there were 3 different draft registrations and lotteries. In the first the draft, about the 10 million the men aged 21 to 30 registered, and some of them served in the military. A year later, in the second the draft, those who just turned into the 21 registered, and some of them served in the military. In the third draft and third and final draft, all remaining men in aged 18 to the 45 registered, but few of them served in the military because the war ended 2 months later. And the fact that the different age groups were drafted at different time that suggests a potential identification strategy based on which portion of inventors in a firm are in different the age groups. So let's figure out what kinds of data set that could tell us which inventors that had which ages at which firms. I create the farm inventor matched pattern data using the information on pattern applications from the past state database. In pattern application, I can identify which inventors had the patterns together with which farms. And to get information on age and geographic location of inventors, I use data from my previous work. We use the fuzzy matching procedure to merge pattern data into the census. Then I collect the data on draft card registration and military service record from familysearch.org. This website is one of the largest historical archives and open to the public. And I match inventors' full name and birth year. And this shows an example of the US draft card registrations on the website. And specifically, I made the Python code to match inventors' full name and birth year on the website with the record in the census. And this summarized how I create the data set. And I first merge pattern data into the census. Then I match it with the draft registration and military service on the website. And on the other hand, I create the form level the pattern data, and eventually I create the form inventor matched pattern data. And this data set allows me to identify and how many inventors in a firm are in a draftable age group, and how many inventors in a firm actually served in the military. And let me describe summary statistics of the data used in the empirical analysis. The sample consists of firms which had at least one patent applications before the draft and had no patents related to the arms industry, such as weapons and explosives. And outcome is the patent applications not related to the arms industry. I dropped the firms and patents related to the arms industry because the firm could experience a large increase in the production, thus increasing the inventions during the war, working closely to the arms industry, and they could be differently affected by the draft. They could appeal the petition to the government, so they were less likely to lose their inventors. And in the table, the first three rows shows the number of patent applications per year, and they experience a large decrease in patent activity during the draft. And next three rows shows the number of inventors in each space. Inventors in collaboration space are defined as those having a patent joined with a firm, that is inventors working with a firm. And inventors in geographic space are those working in the same county where a firm is located. And inventors in idea space are those having a patent with the specific, the particular, the IPC code in which a firm holds the patents. That is working on the same topics in the space of ideas. And then I create the treatment and control groups in each space respectively. In collaboration space, treatment group is firms with a large portion of inventors interactable age group who worked with a firm, and control group is firms with no such inventors. Specifically, I constructed two measures. A portion of inventors who served is calculated by a number of the inventors who served in the military and worked with the firm, divided by the all inventor team members who worked with the firm. And these numbers are weighted by the pre-World War I patents because they could affect differently. I consider the productivity of the inventors and how closely they work together. And a portion of inventors at risk in draftable age group is computed by the number of inventors aged 21 to 30 in draftable age group who worked with the firm divided by all inventor team members. Difference is that I use the draftable age group instead of the actual military service. And this is the identification strategy based on the fact that firms with a large portion of inventors at risk in draftable age groups are more likely to lose inventors due to the draft and military service. And this shock to the labor supply of inventors should affect the firm innovation. And in geographic space, treatment group is firms in same county, in which county's inventors in draftable age group. I construct the measures in the same way. And in idea space, I construct in idea space treatment groups of firms working on the same topics in which those topics of inventors in draftable age groups. In idea space, I use a field composition of firm because the firm could have multiple patterns in multiple fields. And yeah, so the econometric model, the estimate, the measures, the how supply shocks affect the firm innovation using the IB method. And I also explore the dynamics of effect and using this event study specification. And this beta captures the impact at year T relative to the base year of the 1916, a year before the draft. Okay, this table is one of the main tables. In the first three columns, I measure the effect of the supply shocks in each space respectively. And in the last column, I put all supply shocks simultaneously in one regression, so that I measure the marginal effect of the losing inventors in each space. In the first row, a significant negative sign on collaboration space suggests that the losing inventors working with the firm decreases the firm's innovation activity. In the second row, insignificant coefficient on geographic space suggests that there is no significant effect of losing inventors working in the same geographical location. And a positive sign on idea space suggests that when they lose the inventors working in the same industry, in the same space of idea, they increase, firms increase their inventions. Let's suppose the supply shock by the 10%. A 10% decrease in inventors in collaboration space decreases the firm's patterns by 12%, given their dependent variable mean. But a 10% decrease in inventors working in the same the idea of space actually increases their patterns by the 8%. And this the graph shows the estimated coefficients in response to the supply shock in collaboration space using the event study specification. And as you can see, there is the decrease during the draft, and this suggests that there is they experience a decrease in their patterns when they lose inventors working with them. And moreover, this provides evidence of the identifying assumption of the defensive strategy, a common pre-trend. As you can see, the coefficient before the draft are insignificant. And this shows the estimated coefficient in response to the supply shock in geographic space. All coefficients are insignificant, and this suggests that the losing inventors in geographic space does not affect the firm's innovation activity. And this shows the estimated coefficients in response to the loss of inventors in idea space. And this suggests that losing inventors working in the same industry increases the firm's inventions. So far, we look into the overall effect on the all firms, but these effects could vary depending on firms' characteristics. When I use the subsample of the more innovative firms, which had the pre-World War I patterns above the median, I found the consistent result of the main finding. And when I use the another subsample of the less innovative firms, I find that they do not increase the innovation activity in response to the loss of inventors in idea space. It means that they actually decrease their innovation activity when they lose inventors in idea space. This suggests that less innovative firms heavily depends on the knowledge spillovers generated by the inventors working in the same industry. And this is the list of the robustness checks. So I'll just explain the one key the robustness checks. And the key assumption of my identification strategy is outcome of firms with a large portion of inventors in reputable age group, and outcome of firms with outcome of other firms do not change differently in the absence of shock. And this shock to the inventors' labor supply should affect the firm outcome through the military service. Thus, the placebo supply shock of inventors in other age groups, not in the reputable age groups, should not affect the firm's outcome, because the inventors in other age groups were less likely to be drafted and served in the military. And I found the insignificant effect of the placebo supply shock using the IB method and reduced form estimate. And this provides evidence the validity of my instrument based on the draftable age group. And let me explain a couple of the mechanisms through which how inventors affect the farm innovation. And first, the quality of inventors plays a critical role in explaining the farm's innovation activity. And I found that the losing high quality inventors that working with the farm in collaboration space, the firms, when they lose the high quality inventors, that they substantially decrease their innovation activity. But the losing the low quality inventors does not affect the firm's innovation activity significantly. And the interesting finding is that, as you can see, in the second line in each column, so the losing the high quality inventors in geographic space decreases the firm's invention, but the losing low quality inventors in geographic space actually increases the firm's inventions. And the opposite effect canceled out the overall effect of the losing the inventors in geographic space. This explains why there is no significant effect in geographic space.
And you, sorry, could you define, can you specify how you define high quality and low quality inventor, please?
Oh, so the high quality inventors, I use the different specification, but this table, I just used the high inventors, the who had a pre-World War I patents above the median, and the low quality inventors, the who had the pre-World War I patents below the median. Just that I divide the two groups, but I divide by the different groups. Yeah, and yeah, it's important to understand how this supply shock affects over the industry in the long term. So to investigate this, I consider the industry level analysis because the firm could change their names or their location. So I find that the losing inventors in the industry that attracts new inventors and new firms in that industry. Thus, the overall innovation activity in that industry does not change significantly. And I also investigate the peer effect on the inventors, who were not drafted and did not serve in the military. I find that the losing the collaborators decreases their innovation activity. And when I use a subsample of the young inventors, the intractable age group, but not being drafted, and I find that they actually benefit from the loss of inventors in idea space. It means that they increase their innovation activity when their peers in working in the same topics were drafted and served in the military. And when I use a subsample of the old inventors, not in the draftable age group, they suffer from the loss of their collaborators. They decrease their innovation activities when they lose the peer in collaboration space. Okay, let me conclude. So I find the three main results. First, the losing inventors are working with the firm in collaboration space decrease the firm's inventions. The inventors, the human capital, the help the firm, the innovate. And the losing inventors, the outside the firm, the working in the same county, does not affect the firm's innovation activity. I provide the evidence why there is no significant effect using the quality of inventors. And third, I find that the losing the inventors outside the firm working in the same industry, in the same space of ideas, actually increases the firm's inventions. This suggests that when there is a less competition in the industry, the new ideas grow up and the new inventors and new firms enter into the industry. And this effect depends on the firms and inventor qualities. The highly innovative firms create the new ideas when they lose inventors in the space of idea, but less innovative firms heavily depends on knowledge spillovers. So they suffer from the loss of inventors, and the high quality inventors generate a large knowledge spillovers. And my study, the findings suggest the policy implications of how shocks to labor supply and human capital affect the firms and innovation. I find that highly innovative firms and young inventors the benefit, but less innovative firms and old inventors suffers when they lose inventors, and new firms and new inventors the appears in the industry, in the field when there is a less competition. Suppose, let's take an example of the H-1B visa program, which allows US firms to hire the high-skilled immigrants workers. Suppose this visa program ends, what happens to firms' innovation activity? It's unclear which firms are the more affected by this policy change. For example, a large firm such as Google, Facebook could be more affected when they lose inventors, or a small firm such as Silicon Valley startups could be more affected when they lose inventors. I think the findings could suggest some policy implications, but I know that my study is based on the context of the early 20th centuries when the mass production introduced in the US. So I investigate on the current industries and the other areas of knowledge production as a future research to see the when and where the new ideas grow up. Yeah, that's what I have.